Hello, welcome to part 4 of this video lecture from chapter 5. In this part of the lecture, we will talk about ropes, pulleys, and interacting objects. So we're going to start by talking about ropes, strings, and cables. And in order to keep things as simple as possible, we're going to model ropes, strings, and cables as being massless. And really what we're saying here is that the weight or the mass of the rope or string is insignificant compared to the other objects in the problem. And this is often the case in physics problems. So this is the so-called massless string model that we're going to employ here. So the first part says that the tension in the rope, string, or cable is equal along the entire length of the rope, string, or cable. And the second part says that the force applied to one end of the string, rope, or cable is transmitted equally to the other end due to equal tension. So to see what this means with an example, look at this picture down here where we have the guy is pulling this car with a rope attached to it. And so he's pulling with a force of 100 newtons on the rope. So what that means is that this force that's applied to this end of the rope is equal to the tension in the rope. So the tension of the rope is 100 newtons, and that tension is the same everywhere along this rope. So this end of the rope here that's attached to the car, since it has 100 newtons of tension, the car feels a force of 100 newtons applied to the car. So kind of another way of saying this is that the purpose of a rope, string, or cable is to transmit a force from one end over here to the other end over here. Here's a nice little conceptual quiz for you to think about. So the question is, which rope in these pictures here has more tension? So in this first scenario, A, we have the guy here pulling on a rope that's attached to the wall, and he's pulling with a force of 100 newtons. So the question is, how much tension is in this rope? All right. For part B here, the other scenario is where the guy and the girl are having a tug of war, and he's pulling to the left with 100 newtons. She's pulling to the right with 100 newtons of force. So what is the tension in this case? So think about this for a minute. Maybe you want to pause the video and think about which one of these ropes, A or B, has more tension and why. Well, the answer is neither. Both ropes have the same tension of 100 newtons. Now, some of you may have thought that this rope here would have a tension of 200 newtons because he's pulling to the left with 100, she's pulling to the right with 100, and we're going to somehow add those together to get a tension of 200. But that's incorrect. In fact, this situation here is exactly the same as the situation here. Because think about our model of the massless string model. We have a rope here with 100 newtons of tension in it, okay, because that's how much he's pulling with. Well, that force is applied to the wall. So the wall feels a tension of 100 newtons pulling on it. But by Newton's third law, if the wall is being pulled by the rope, then the rope is also being pulled by the wall with an equal force of 100 newtons. So in part A here, this rope right here has a 100 Newton force pulling it to the right, caused by the wall. And so in both cases, the rope has a 100 Newton force pulling to the left on one end and 100 newtons to the right on the other end. And the total force in the rope is just the tension of 100 newtons. Let's now turn to pulleys. So strings, ropes, and cables often pass over an object called a pulley. It's basically a simple machine. In this chapter, we're going to assume that the pulley has no mass and no friction. Now, this is something we're going to look at later in the course where we talk about a pulley with mass. But the way a pulley works is it's just a way to transmit force and change the direction of the force. So we see this guy here, he's lifting up this box, and the box might be, heavy, maybe too heavy for him to lift by himself, but when he uses this pulley, he can use his own weight and sort of hang on the rope, and that might allow him to be stronger and lift up the box in this way. So whatever he's pulling with over here, that tension is transmitted around the pulley and to the box here, okay? So the idea here, the massless pulley and string model has the following characteristics. Number one, the tension in a string is constant as it passes over the pulley. All right, so if this, in this picture here, if you're pulling on this rope with a force of 50 newtons, then the tension in the rope right here is 50 newtons. Well, that 50 newtons is also the same over here on the other side of the pulley. So there's constant tension along the rope, no matter what angle or how much the rope bends here, it's the same tension here. The force applied to one end of the string, rope, or cable is transmitted equally to the other end due to the equal tension. So this weight down here feels a tension force of 50 newtons upward due to this rope, and that 50 newtons came from the hand here pulling with that 50 newtons. So let's start with a real basic example. You pull on the rope in this picture here with a force of 30 newtons. The question is, what is the acceleration of the 2 kilogram mass? So, as you pull this string, presumably this mass is going to rise up, and we're going to try to figure out what the acceleration is. So the best thing to do here is start with a free body diagram, as always. So let's draw a free body diagram just for this mass right here, the 2 kilogram mass. So that's represented by the dot right here. Now, what does the mass feel? Well, the mass, of course, has weight, mg, pointing down, and then the mass has tension. It feels the tension force pulling it upwards. So these are the two forces. So the question is, how much is this tension force? Well, the tension, remember, is the same everywhere along the rope, and it's equal to the force that's applied to it over here. So the tension is equal to 30 newtons. So we can now apply Newton's second law. The net force equals ma. So from this diagram, we have tension up minus mg down, and that's equal to ma. We can solve for acceleration by dividing by m. So we have acceleration is equal to t minus mg over m. And now we can plug in our numbers. The tension, remember, is 30 newtons, and m is 2 kilograms, g is 9.8, and on the bottom, there's the mass again, which is 2. So when you calculate this with your calculator, you'll come up with an acceleration of 5.2 meters per second squared. And again, the sign here is positive, so that just reinforces the idea that this mass is going to move upward. It's going to accelerate in the upward direction because we call the positive direction up. Things get much more interesting and challenging when we have two objects connected by a rope and a pulley. So this is our first example of what are called interacting objects. So look at this picture here, which describes the situation. We have two masses, two blocks, block A up here, block B hanging down here from a rope that goes over a pulley and connects the two blocks together. Furthermore, for this problem, we're told that this surface up here is frictionless. So this would be, for example, a real smooth or slippery surface like ice or something like that on top of the table. We're told that the mass of A is 10 kilograms and the mass of B is 5 kilograms. And so the question is, will the blocks shown below move? That's the first question. And if so, calculate the acceleration of block A and block B. All right, so to do this problem, there is definitely a hard way and an easy way to do this problem. And kind of surprisingly, your textbook only describes the hard, long way to solve this problem. I'm going to show you a much, much faster and easier way to do these types of problems. That'll save you a lot of time and probably save you from making a lot of errors and mistakes along the way. So the first thing we can do before we actually do any math or use formulas is let's just try to figure out if this thing will move at all. Now, obviously, this block here has more mass. In fact, it's twice as massive as this one down here. So at first glance, you might think that, oh, well, no, this one can't move because, you know, this one's heavier than this one. But that's not the way to approach this. Think about block A, what it feels. Well, block A feels the tension in the rope from block B pulling on it. I don't care how light block B is. As long as there's something hanging here on the rope, this rope has tension. So block A feels a force pulling it to the right, and there's no friction at all. So A has to move. Now, it may move very slowly. You know, if A has a lot of mass and the tension is very small, then its acceleration is going to be tiny, but it will absolutely move in every case, no matter what the masses are of A and B. The next thing just to talk about here before we get into the details is that whenever we have interacting objects, there's something going on here in that the motion of the objects is correlated to each other. In other words, A and B do not move independently. They move together or in concert. So, and that is because they're connected by a tight rope. And this rope doesn't stretch. We're going to assume it's, you know, a non-elastic type of rope or cable or string. So what that means, if B were to move downward by, let's say, 1 centimeter, well, then A has to move to the right by 1 centimeter. Likewise, you know, if A up here moves to the right by 5 centimeters, then B has to drop down 5 centimeters. So these two movements here are correlated with each other and they're dependent on each other. And we're going to take advantage of this fact to make solving this problem much easier. So as I mentioned, there's an easy way and a hard way to do this problem. So your book explains how to do this problem the hard way, which I'm not going to go through. But basically, it has you draw a free body diagram for each block, block A, and for block B, labeling all the forces. And then it has you solve Newton's second law in the horizontal direction, which are all these steps here, and then in the vertical direction, all these steps here, and finally, basically substituting results together to get the final result. And if you count all the steps here, including, you know, the free body diagrams, it's 14 or 15 steps to get the correct answer, which is 3.27 meters per second. There's a much, much easier way to do this, which is what we're going to focus on next. So the shortcut method to doing this is much more direct, and it involves a couple of tricks here. The first step is we're going to combine both masses together as a single system that has a total mass of m sub A plus m sub B. All right, so we have mass A here, we have mass B here, but remember these masses move together as a system. They're not moving independently. And so because of that, we're going to use the total system mass, MA plus MB. And the other thing is whatever the acceleration of block A is, block B has to accelerate with the same acceleration. And again, the reason for this is that they are attached by a tight rope that can't stretch. So the motion of A correlates precisely and exactly to the motion of B. The only difference, of course, is that A moves to the right and B moves downward. But they move in those directions with the same acceleration A. So there's only one acceleration in this problem. All right, the single system moves along the direction shown by the curved red arrow. So normally, you know, we think about directions as either, you know, A is moving horizontal and B is moving vertical. Well, what we're going to kind of do here is we're going to consider the direction of our system. It moves to the right up here and it moves downward here. So we sort of have a curved direction. This arrow represents the positive direction of motion of our system. all right? And our acceleration, right, is going to be along this arrow as well. Up here, it's going to be to the right, and down here, it's going to be going downward. Now, here's one of the reasons this saves us so much time and headache. We can ignore the tension forces of the rope. In other words, this tension force here and this tension force here magically can be ignored. Now, that seems like that's in violation of some law of physics, right? Because we know this rope is pulling on A, so how can we ignore it? Well, the reason for this is these forces, these tension forces, are internal to the system and they cancel out, all right? In other words, this tension force on A is pointing to the right up here, which is in the positive direction. But the tension force down here on B is pointing upwards, right? The rope is pulling B in the upwards direction. That is a negative tension. And remember that the tension along the rope has to be equal everywhere. That's one of our rules for the model of tension in a rope. So these two tensions are equal and opposite. Therefore, they're going to cancel anyway. So we can just ignore them. It's a clever trick and it saves us a lot of time. So the only forces that act on the system that we need to worry about are forces along the direction of motion or opposite to the direction of motion. All right, so here's where we just have to be a little careful now. We have to think of, here's our system. Remember, it's A and B connected together. For A up here, are there any forces that work along the horizontal direction? Now, of course, there's tension, but remember, we're ignoring tension because it gets canceled. So ignoring tension, the only other force that would be along this direction would be friction. But remember, in this problem here, so far, we're talking about a frictionless table. So A has no force external to it, all right? There's this internal force that we're going to ignore. All right, now for B, the situation is different. Again, we ignore the tension force, but B has gravity pulling it downward, and gravity pulls in the direction of the motion over here, all right? We don't include gravity up here because A is moving left and right, and gravity is not in that direction. But for B, we absolutely have to include the force of gravity acting on B. So the force of gravity on B is the mass of B times G, mg, all right? So we can now apply Newton's second law. Net force is equal to the total system mass times acceleration, F equals ma. The net force is just this force here that we identified. So it's the mass of B times G. The total system mass is A plus B, the masses of A and B together, and then we multiply that by the acceleration. So we're going to solve for A, the acceleration, so we divide by the total mass here, ma plus mb. So our acceleration is m sub b times g. So let's plug in our numbers. The mass of B, remember, was 5 kilograms. G is 9.8. Down on the bottom, we have the mass of A plus B. So the mass of A was 10 kilograms, the mass of B, 5 kilograms. And if you calculate this in your calculator, we will get the exact same answer, correct answer of 3.27 meters per second squared. So once you get the feel of how to do these steps over here, you can see this problem is really solved in 3 relatively simple steps. You can maybe argue there's a 4th step here because we have to identify this force. But this is at least 3 times faster than the previous method. We can modify this problem a little bit, make it a little more difficult, and include friction in the problem. So we have the same exact setup here with the 2 masses A and B connected by a rope over a pulley. The only difference now is that the table has friction and the coefficient of kinetic friction is given to us as 0.2. So the question is, will the blocks still slide? And if they do, calculate the acceleration of block A and block B. So the only difference in this problem now is that now we have to include a friction force acting on our system, because this friction force is, pulling to the left, and that's in the direction of motion here. So that's going to affect the motion of our system. And of course, we still have to include the weight force of block B, m sub bg, because that mass is, that weight force is what's pulling the system and making it move. So other than that, we proceed as usual. We can write Newton's second law. the net force is equal to the total mass times acceleration. And now by looking at our picture here, we have to write the net force. So remember, our direction of positive motion is along this curved arrow here, because this is the direction that the system is going to move. So this force here, mg here for block B, is a positive force because it is pointing along our positive direction. Okay, we assign this downward direction as positive. The friction force, however, is pointing to the left, whereas block A is going to move to the right. So this friction force is in the opposite direction. So our total net force is m sub b g minus the kinetic friction force. And then on the right side, everything is the same as in the last problem. We just add the two masses together and multiply by the acceleration a. The next thing we can do here is the friction force, as always, is equal to mu times mg, which is the normal force of block A. All right, remember, block A is moving horizontally. It's not moving up or down. So the normal force on block A is equal to its weight. And its weight is m sub A times g. So here we have our total equation written out. This is Newton's second law. This is the net force on the left, and this is the mass times acceleration. And then we solve for A, kind of like we did on the last page. We just divide everything by the total mass here, plug in all our numbers, and we end up with an acceleration of 1.96 meters per second squared. So in the previous problem, we had an acceleration of 3.2 meters per second squared. Obviously, the acceleration is less now. Why is that? Well, because there's friction. Right? This thing is not going to slide as fast because this friction force opposes the motion. As I mentioned previously, the last couple of examples were what we call interacting objects. That's the picture shown over here, where the push or pull on each other due to direct contact or connection by ropes, or you can have other contact. They can be in direct contact or with a spring or something like that. So these are a couple other pictures of examples of interacting objects. We're going to do a problem like this next. This one here, we won't be working on this one, but you can see that these two objects are sitting on top of each other, connected by a spring down here. So your book, again, explains how to solve interacting object problems, and it does it, it explains it using the long, hard method, which I don't recommend at all. These are the steps here. Let's go ahead and let me show you the shorter, much more quicker method. So the shortcut method, which I would highly recommend, is to do this. We model the entire system as a single object with a total single mass. So remember how we added these masses together to find the system mass? Well, we're going to do the same thing in this case, or we would in this case as well. And then one of the key steps, the tricks here, is to ignore the internal forces between objects since they cancel out. Only include external forces that act along or opposite the direction of motion. All right, and so we'll run through an example shortly. And then we can apply Newton's second law to the entire system to find the system's acceleration. So remember that these two blocks, A and B, they have the exact same acceleration. These two blocks, A and B, which are being pushed to the right, they have the same acceleration because they're moving together. They're moving as one object. And then finally, we can apply Newton's second law to individual objects within the system, if needed, to find any forces acting on them. And again, the trick to remember is that all objects in these systems here have the same acceleration. Let's go ahead and look at an example. So this example here is the picture here was showing a hand sliding two blocks, A and B, across the table. You push on block A with a force of 5 newtons. So that's the force applied by your hand. Block A's mass is 2 kilograms, that's a small guy. And block B's mass is 6 kilograms, that's the large mass. And we're going to assume the table is frictionless in this case. So the question is, determine the force by which block A pushes on block B. So obviously, just looking at this picture here, the reason block B moves is not because of the hand pushing it, but because A is in contact with it and pushing it, okay? Now, again, the hard method to solve this is the way your book does it. And I'm not going to spend our time or energy, going through the detailed, difficult solution. But, again, it has you drawing individual free body diagrams for both blocks, identifying force pairs, and then going through a whole bunch of calculations for each block and so forth. And you can, again, if you count up all the steps here, I think it's close to 15 steps to get to the final answer, which is 3.75 newtons. Well, we can get this same answer much, much more quickly. Let's see how to do this. So instead of doing all those steps shown on the last slide, we can figure out and get the same answer using basically just 2 steps. All right, so what's the trick here? Well, what we're going to do here is first of all, find the system acceleration of both these blocks together. All right, and that's relatively easy. We say net force is equal to ma, where m is the total system mass of A and B added together. So the acceleration of our system is equal to the net force. And remember, the only thing pushing on this system here is the hand. There's no friction, all right? It's frictionless. There are no other forces in the horizontal direction, all right? There's gravity down, normal force up, but we can ignore those. They cancel each other out anyway, since the blocks don't move vertically. So the only force in the horizontal direction is due to the hand, and that's the net force, which is given as 5 newtons. And then down on the bottom, simply we just add the 2 masses together. Remember, this is 2 kilograms and this is 6 kilograms. So we have 5 divided by 8, which is 0.625 meters per second squared. So we know now what the system's acceleration is. So the question is, determine the force by which block A pushes on block B. Well, if we think now about block B all by itself, Newton's second law has to hold true for block B. So the net force on block B is equal to block B's mass times its acceleration. Well, block B, remember, has a mass of 6, and we know that block B accelerates with this number here, 0.625, because that's the system's acceleration. So 6 times 0.6275 is 3.75, and that's the same answer shown on the previous slide, which took something like 15 steps to get to. So obviously, this is a much more efficient method for solving these types of problems. Okay, that is all for Chapter 5. We will see you soon, and we'll continue on with Chapter 6.